Swayam Prabha. Digital India. Educated India.
Welcome back to the lecture series in Bioenergetics. So, in the last class, the 8th lecture or the 3rd lecture of the 2nd week, we talked about the classification of different bacteria, eubacteria and archibacteria, and we talked about the iron sulfur bacteria, we talked about methanogens, we talked about the bacteria which are loving the extreme salt environment, and then with the eubacteria we talked about gram positive bacteria, we talked about photosynthetic bacteria which have evolved in the anaerobic conditions, we talked about the bacteria which like blue green algae or the cyanobacteria, we talked about the purple photosynthetic bacteria, and we talked about the spirochetes. So, what essentially we highlighted there was the light dependent and chemical dependent synthesis of molecules. So, today we will talk about the basic parameters of thermodynamical parameters, which in the first week we covered a little bit, and I kind of giving a gap to pick these up because these are some of the concepts, and what I personally believe that these concepts should get into your system slowly, so that you get time to digest and kind of figure it out, okay, this is what is happening. So, let us start the lecture 9, which is lecture 9, or we are into week 2, lecture 4 of week 2. So, W2 L4. So, today we will be talking about the importance of free energy for the cell. Okay. The importance of free energy. We have talked about a lot about delta G. So, today we will talk about a little bit more free energy for cells, delta G. So, whenever a reaction occurs, so we have talked a lot about the self assembling. So, if you go back, so this was one of the slides what I wanted to highlight here. If you follow this blue box, okay, if you follow this blue box, this blue box is, so this process of self assembling, whether it will happen or not is a function of whether it will happen spontaneously or you need to infuse energy into the process, depends on this parameter, the free energy. If free energy is negative, it means it will happen spontaneously, and if free energy is positive, it means you have to put energy into the system. So, today in the light of that, we will talk about the significance or the importance of free energy for the cell. The life is possible because of the complex network of interacting chemical reactions occurring in every cell. In viewing the metabolic pathways that comprise this network, one might suspect that the cell has had the ability to evolve an enzyme to carry out any of these reactions that it needs, but this is not so. Although enzymes are powerful catalysts, they can speed up only those reactions which are thermodynamically feasible, those which are thermodynamically feasible or thermodynamically possible. Okay. Other reactions proceed in cells only because they are coupled with favorable reactions to drive them. The other way, as I told you, that either delta G will be positive or delta G will be negative, and if it is negative, that this is a spontaneous reaction, and if it is delta G is positive, you need energy input. And energy input in terms of coupled to favorable reactions to drive it, and we will come later about it. Coupled to favorable reactions to drive it. Okay. So, when we talked about coupled to a favorable reaction to drive it, this is very significant because biology will observe this is, and this will come time and again. So, it will be something like that. Say for example, a reaction say A to B has to occur, and that is an energy intensive process. You will see this reaction will be coupled with another reaction which will ensure that, so this may be X to Y. So, this coupling is a common process in biological modules. This is not something which is seen somewhere else, but in the biological world, in the world of life we are, this kind of coupled reactions are extremely important. Okay. So, coming back about the delta G and in thermodynamics, the question is whether a reaction can occur spontaneously or instead that needs to be coupled to another reaction, and especially this coupling happens when delta G is positive, okay, is central to most of the things. The answer is obtained by reference to a quantity called free energy. The total, in other words, the total change in free energy during a set of reaction determines whether or not the entire reaction sequence can occur. So, what essentially is that this thermodynamic parameter delta G is exceptionally critical for you to realize whether it is spontaneous. The take home message is whether it is a spontaneous reaction or whether it is coupled with something, because it is a positive. It needs an energy input, and energy released by change in chemical bonding is converted into heat. This is the next concept. What is important is, that is where the enthalpy and the entropy concept comes, is energy released by changes in chemical bonding is converted into heat. So, energy released by changes in chemical bonding is converted into heat. So, in other words, a molecule A is converted into B. Okay. So, the energy released by the change in the chemical bonding, part of it is liberated as heat. This concepts is really essential for us to appreciate, because as we will move through, you will realize. So, where this whole concept comes into play is, whenever we talk about an engine, a cycle or energy involvement, we always talk about that how much energy is lost in the form of heat. Whenever there is a conversion, whatsoever, it's an inorganic world, organic world, bioorganic world, or the world of petrol, or the energy rich molecules in terms of like inflammable gas. So, we always talk about how much in that conversion it is lost as a heat. So, as a matter of fact, most of this process one needs to really, so whenever there is an change in the chemical bonding pattern, so some double bond become a single bond, or likewise so forth, there is some energy which is converted. So, there is never an absolute conversion of energy. So, if for example, I say I started with 8 unit, okay, and a part of it will be lost while conversion, or something will be lost as heat. So, there the efficiency of an engine, efficiency of a conversion, the energetics efficiency is considered in a situation by the basis of what is the least amount of heat which is liberated. A efficient system is the one which liberate extremely low amount of heat as compared to a system which liberates a lot of heat. So, what is the amount of heat which lost in that whole process says that the system is not energy efficient, because because the problem is you have to always realize. So, say for example, your brain does, like, try to understand it by an analogy, a different kind of analogy. Your brain is processing information at a rapid pace. A computer is doing the same thing. You are running processors after processors in a computer, you are adding processors and everything, and it is converting. But a computer gets heated up if you keep on increasing the number of processors, right? Whereas you think so many things, still your brain can withstand. So, biological modules, what have evolved over the years, over billions of years, have ensured that the evolution of heat could be compensated some way or other. But energy released by changes in the chemical bonding is converted into heat. That is a common phenomena, and based on that, if you some way or other can quantify this heat, then you can tell about the efficiency of that conversion. The lesser the heat evolved, the more is the efficient conversion into it, or rather maximum utilization of the energy. Okay. So, say for example, ATP molecule gets broken down, say to ADP and eventually to AMP. Okay. So, in this whole process there is energy which is released, and some form of heat is also released during this process. So, depending on which molecule liberates least amount of heat, one can say that how efficiently it is converting into the process. Okay. So, this is one concept which I will be talking further in the next class, where we will talk about energy released by chemical changes, chemical bonding. Energy released by the changes in the chemical bonding is converted into heat. So, and in order to understand, like, this is something like this. So, for example, an enclosed system, if you consider an enclosed system like this, okay, and here you have a box, and here you have a cell, and here you have a C, and here you have the universe. Okay. Now, an enclosed system is defined as a collection of molecules that does not exchange matter with rest of the universe. Okay. So, this is an enclosed system what we are talking about. Okay. So, enclosed system is defined as collection of molecules enclosed system is defined as collection of molecules that does not exchange matter with rest of the universe. So, keep that in mind, it does not exchange any matter with rest of the universe. Okay. For example, this is a case of a cell in a box. Okay. Any such system will contain molecules with a total energy of E. Okay. Such system will have a total energy of E. Okay. Any such system will have, and always remember that this is not exchanging any molecules from outside, total energy of E. Okay. This energy will be distributed in a variety of ways, some as translational energy of the molecule, some as the vibrational energy, some of the rotational energy, but most of that will be the bonding energy between the individual atoms that make up the molecules. Okay. So, this will have your, let us enumerate the energies just in case you forget: vibrational, rotational, and the bonding, and the major chunk will be the bonding. These will be the minor ones, okay, that makes up the molecule. Suppose that a reaction occurs in the system. The first law of thermodynamics places a constraint on what type of reaction can occur in the system. It states that in any process, the total energy of the universe remains constant, or whatever be the process. This is what the first law of thermodynamics says very clearly. First law of thermodynamics, that total energy of the system remains constant. Keep this in mind. This is essentially what the first law of thermodynamics states. For example, suppose there is a reaction between A to B occurs in an enclosed system which release a great deal of chemical bond energy. This is what is being released. We are trying to talk about this released chemical bond energy because of the breaking or the making of the bonds. Okay. This energy will initially increase, and the intensity of molecular motion, translational, vibrational and rotational in the system, which is equivalent to raising its temperature. However, these increased motions will soon be transferred out of the system by a series of molecular collision that heat up first the walls of the box and then the outside world. So, what will happen? So, there will be a lot of collision of the molecules. So, this is going to heat up the kind of hit upon these, and this will eventually get transferred outside in the form of heat. And then outside world represented by the C for in our example. In the end, the system returns to its initial temperature, by which time all the chemical bond energy released in the box has been converted into heat energy. So, there will be a rise in temperature and then eventually it will fall, but in this whole process most of the heat energy, most of the bond energy is converted into heat energy, and transferred out of the box to the surrounding. So, according to the first law of change in the energy in the box. So, if I talk about delta E of the box, okay, which we shall denote by delta E must be equal and opposite to the amount of heat energy transferred, and it could be designated as delta E is equal to minus H, which is essentially the change, which is the heat energy, that the energy E in the box, the energy in the box E decreases when heat leaves the system. So, in other words, when the heat energy is going out, as the heat energy is moving out of the system, so what is happening out here, there is a, this leads to a lowering of energy of the system. Okay. So, I will close in here, I will pick it up from here. What are the connotations and how we will move on to the second law and the entropy and the Gibbs free energy from here. So, just for the time being, just try to realize there is a reaction happening out here, and that leads to generation of heat, generation of the molecules kind of getting disturbed, and they generate heat, and that heat moves out of the system, and in that process system lowers its energy. We will follow it up from here, and we will move on to the second law of thermodynamics, to the entropy and the Gibbs free energy, what we promised each other in this section. If you go back here, free energy, entropy, enthalpy, generation of heat, this fundamental drawing, remember it. Okay. In the next class, we will follow it up from here. Thank you.